7.35, we say they have an acidosis. If it's above, we say they have an alkalosis. So when you look at gases, the first thing you do is look at the pH and determine, in fact, if there is an imbalance, and if so, what type is it? Now, the fact is, we're constantly bombarding our bloodstream with acid. For instance, in pharmacology, you learn that pharmaceutical companies, when they manufacture a drug, they typically create it as either a weak acid or a weak base. And so if it's an acid, when it enters into the bloodstream, it releases hydrogen ions. If that drug is a base, it soaks up hydrogen ions, which can result in a shift in the pH of the blood. By the same token, many of the foods and beverages that we ingest are acidic. For instance, if they're not acidic, they're converted into an acid, like alcohol. It's converted to acetic acid. You know that a lot of fruits are made up of citric acid. In addition, through metabolism, we produce acids. Many proteins contain phosphate groups, okay? And some of those proteins are converted, for instance, to phosphoric acid. We produce lactic acid as a result of anaerobic metabolism. If we break down fats, for instance, if we haven't had anything to eat in a while, and our body starts breaking down triglycerides, we produce ketones, some of which are acids, so we call those keto acids. But when we break down triglycerides, we also form fatty acids. Well, by definition, all of these molecules release hydrogen. And then CO2, if it goes up in our bloodstream, can be converted into hydrogen. I think that is respiratory acid. I guess the point I'm getting at is that you would think with all of these acids that we're dumping into the bloodstream, that our pH would begin to fall. Okay? But the fact is that there are homeostatic mechanisms that serve to maintain the pH within that relatively narrow range between 7.35 and 7.45. These homeostatic mechanisms are buffering systems. Buffering systems serve to resist a change in pH, which would otherwise occur if those buffering systems weren't in place. And this is a list of the three major buffering systems. And it's kind of a list in order of how rapidly they act. Chemical buffers act more rapidly in the respiratory system, which acts more rapidly than renal mechanisms. On the other hand, it's also in order of strength. Chemical buffers are relatively weaker than the respiratory system, which is weaker than renal mechanisms. So, we go from fastest acting to slowest acting, from weakest to most potent. Chemical buffers act within seconds to resist a change in pH. Why? Because chemical buffers are already there in place within the bloodstream to act immediately. The respiratory system can react to a change in pH. That generally takes minutes, whereas renal mechanisms can take hours to days. So they're slowest. Chemical buffering systems usually consist of 1 or 2 molecules, okay, that act to resist a change in pH when either a strong acid or a strong base is added to the bloodstream. Now, there are several chemical buffering systems, the most important of which is the bicarbonate buffering system. It consists of 2 molecules that are in equilibrium. It consists of carbonic acid and its conjugate base, sodium bicarbonate. Okay. They exist in equilibrium. Now, what we're going to discuss now is what happens when a strong acid or a strong base is added to the bloodstream. But before we can do that, let's differentiate between a strong acid and a weak acid. Hydrochloric acid is a strong acid, meaning that when it's dissolved in water, it completely dissociates. So if I had 10 molecules of hydrochloric acid that I dissolved in a certain volume of water, I would have 10 free ions of hydrogen, which would result in a significant drop in pH. On the other hand, if I had the same quantity of a weaker acid, like carbonic acid, when I dissolve it in water, it does not completely dissociate. So if I had 10 molecules of carbonic acid and I dumped them in the water, that quantity of carbonic acid may only release 4 ions of hydrogen, which would result in a much lesser drop in pH. So stronger acids completely dissociate, weaker acids only partially. So let's see how this bicarbonate buffer system works. Let's suppose I added a strong acid, like hydrochloric acid, to the bloodstream. We said that hydrochloric acid, when it's added to the bloodstream, is going to completely dissociate into hydrogen and chloride. Okay. That has the potential to result in a marked drop in pH. But what's going to happen is then that hydrogen ion is going to react with sodium bicarbonate. And when it does so, sodium bicarbonate is converted to carbonic acid. So I have converted a strong acid into a weaker one. If I had 10 molecules of hydrochloric acid, instead of there being 10 free hydrogen ions now dissolved within the plasma, I will only have 4. So in effect, by converting hydrochloric acid into a weaker acid, I have a lesser drop in pH. It's blunted the drop in pH that would otherwise occur. Are we all good with that? Now, a strong base is one that completely dissociates. Okay, and when it does so, it grabs onto each of the basic molecules, grabs on a hydrogen, removing a hydrogen from the bloodstream. So let's see what happens now when I add a strong base like sodium hydroxide. In solution, it completely dissociates the sodium and hydroxide ions. Now, the hydroxide is going to soak up a hydrogen from carbonic acid. It's going to react. Good. And removing a hydrogen ion, okay, it's going to convert that carbonic acid, okay, into bicarbonate, which is going to combine with the sodium to form sodium bicarbonate. So we're going to go in this direction like this. Now, what happens to the hydroxide group? When it combines with hydrogen, it's going to form water. So, as a result of that reaction, we're converting a strong base into a weaker base. Okay. So this base is not going to remove as many free hydrogens from the bloodstream as this one would. Okay. So it's blunting any change in pH that would otherwise occur as a result of the loss of hydrogen ions. Now, I'm not going to go through each of these different types of chemical buffers, but the concept's all the same. So, the bicarbonate buffering system is the major chemical buffering system in the body. Bicarbonate can be produced within the kidneys or reabsorbed by the kidneys. So it's made available through activities within the kidney, and so when we dump hydrogen ions into the blood, it can react, forming carbonic acid. We can convert stronger to weak. Now, carbonic acid in the interim can dissociate into water and CO2, and through respiration we can blow off the CO2. So in effect, this hydrogen ion, which was released, it's converted to water. So when we do blood gases, we assess bicarbonate levels because that tells us something about the buffering capacity of our blood. All right. This is the famous respiratory equation here. You know, I've seen this before, huh? We've done this already. CO2 plus water can react to form carbonic acid. Then to dissociate into hydrogen and bicarbonate. Did we talk about Le Chatelier's principle?
Yeah.
Last time, I think, right? If there's a disturbance in the equilibrium, then the reaction is going to move in such a direction as to reestablish a new equilibrium. So if there's an excess of substrates here, it's going to cause this reaction to move from right to left. Same thing would happen if there's a loss of substrate. The reaction would move right to left to replace what's lost. Okay. Let's suppose we had an acidosis, a metabolic acidosis, where we were releasing excessive hydrogen ions into the bloodstream. Okay. That's going to cause a drop in pH. Now, that excess in substrate on the right side of the equation is going to favor the reaction of the hydrogen with the bicarb to produce carbonic acid, which then dissociates into CO2 and water. Okay, that's Le Chatelier's principle. At the same time, the drop in pH is going to stimulate an increase in the depth and rate of respiration. Okay, it's going to trigger that respiratory reflex. Remember, the three triggers are drop in pH, an increase in CO2, or hypoxemia. All right. So as we're producing more CO2 as a result of this reaction, right to left, then we're blowing it off. Okay. Now, it's not only because of the low pH, but as this reaction moves right to left, we start to produce more CO2, and that's a second stimulus for the respiratory drive, which forces us to get rid of that excess CO2. But the idea is, when this reaction proceeds right to left, what happens to the drop in pH? It's blunted. It starts to come back up a little bit, back toward normal. So this is a buffering system that helps to resist changes in pH. Now let's suppose that if instead of having an acidosis, we have an alkalosis. Okay. Well, then the situation is just the opposite. A drop in pH triggers the respiratory reflex. An increase in pH inhibits. So if we have an alkalosis, a relative decrease in hydrogen ion concentration, which is going to be associated with an increase in pH, that's going to inhibit ventilation. And so if we inhibit ventilation, what happens to CO2 levels? Hypoventilation leads to hypercapnia, because we're not blowing off the CO2. So as CO2 levels climb, what does that do? Le Chatelier's principle. It forces this equation then left to right, and what do we start to do? Produce more hydrogen. Okay? And as we produce more hydrogen, we bring down this high pH back toward normal. Now, typically with compensatory mechanisms, you never quite bring the pH back to normal, absolute normal. Okay? It's rare that we would bring this, for instance, all the way back to 7.4, but it makes it close. And we never overcompensate. Now, how do kidneys serve as a buffering mechanism? I'm going to create what some folks may call a Venn diagram. Okay. The kidneys are capable of secreting hydrogen, ions, into the urine. And when they do so, they reabsorb bicarb. Everybody with me? Now, in the face of an acidosis, the kidney's secretion of hydrogen increases, and its reabsorption of bicarb, which is buffer, increases. So if you're getting rid of some of that excess hydrogen, and then you're reabsorbing buffer, which then can also react with the hydrogen that's still there, you're going to tend to bring the pH of the blood back up or normal. That's renal, or some people call it metabolic compensation. Now, the opposite happens with an alkalosis. If the pH is too darn high, what do the kidneys do? They decrease secretion of hydrogen. In other words, they hold on to hydrogen, because that will help to counter that alkalosis, and they decrease reabsorption of bicarb. In other words, you excrete more bicarb because there's no need for increased buffering capacity. Okay. You already have too few hydrogen ions, so you allow some of that bicarb to escape. Okay. That's the renal buffering system. Any questions?
In the last slide, you said the pH is never, it's not overcompensated or...
Right. In other words, if you have an acidosis, those buffering mechanisms will never create an alkalosis.
Okay.
Okay? They'll only serve to bring your pH back toward normal. Everybody's good?